Thank you very much. Am I audible?
Yeah.
All right. Thank you very much. Thank you, Vidamar, for a short introduction and also talking a little bit about what we are going to do today. So yes, we are trying to see the whole statistical approach on a particular data set. And that is actually we want to understand what is the relation between the demographic factors, lifestyle, and metabolic health. So let me begin with the content here. So the data set that I have available here today is from the National Health and Nutrition Examination Survey. It is a program conducted by the National Center for Health and Statistics, which is known as NCHS, and it is a part of the Centers for Disease Control and Prevention. It is known as CDC in the United States. So the data set is from 2013, 2014, and in my data set, the sample size is 2278 by 10. So I have the observations of 2278 with the 10 different columns. All right. So the objective is, of course, to understand the interplay between the demographics, lifestyles, and metabolic health. And to understand those things, the key variables here are the demographics, where I have the age and gender. The lifestyle is physical activities label. So the label means the physical activities like the sports or gyms, how the respondents are involved in, what level of physical activities they are involved in. There are two different labels, level 1 and level 2. So they are categorically assigned on this particular variable. And health metrics, of course, there is BMI, glucose, and glucose is after fasting, and oral and insulin level and diabetes status. Right? And the method that I'm going to use on this particular study is the ANOVA and ANCOVA with a lot of statistics and post-hoc test. So these are all the methods applied for this research. And the goal is, of course, to inform data-driven public health strategies to mitigate disease prevalence and promote overall population health. This goal is, of course, the actionable, right? So it focuses on chronic disease risk factors and aligns with the data set scopes to support public health objectives. So here we go. The first thing is that we did a little bit of explanatory data analysis, where there were a range of data sets that they were actually beyond the realistic average of the data set. So I have filtered the data set some way with the range. The range of the age variable here is between 0 to 120, BMI is 10 to 60, and so on. Others outside of this range are removed from the dataset. So the dataset looks like the respondent age, the first variable. We can see the image shows three plots summarizing the age distribution of respondents. The box plot indicates a symmetric distribution, right, with no outliers and a median around 35 to 40 that we can visually see here. And the histograms reveals a higher frequency of younger respondents. The younger respondents I am referring here is 10 to 20 years. And relatively, it is even distribution across the age groups, right? It's tapering the slightly at older age, about 60 to 80 years. And the third figure that the image shows as the QQ plot that suggests the distribution is roughly normal, but with heavier tails, right? So indicating some deviation at the extreme values. So overall, the data set captures a broad age range with a slight overrepresentations of younger individuals. Right? So this is the overview of my age variable. And here you see the body mass index, the BMI. And the box plot in the left panel here, you can see the box shows a slightly skewed BMI distribution with several outliers, right? So above 40 kilogram per meter squared, suggesting the presence of individual with obesity. So the median BMI is around 27 to 30 kilogram per square, and then the IQ captures the typical range, right? So in the histogram, which is in the middle panel here, it reveals a right skewed kind of distribution with most BMI values clustering between 20 and 13 roughly, and there are fewer cases above 40 as well. So in the QQ plot that usually we do it for checking the normality, and this shows significant deviation from the normality, right? So it's especially in the upper tail here, confirming is the right skewed, seen even in the histogram and presence of high BMI outlier. All right. So the glucose level. So the glucose after fasting, the fasting glucose data is heavily right skewed with most values after the normal threshold of 100, right? And significant number of high glucose outliers, it actually indicative of potential metabolic or chronic condition. Let me go a little quicker for these things now. So there is the insulin level, and the data looks like these levels are heavily right skewed again, and with most values in the normal to slightly elevated actually from the range, and notable high outliers indicative of insulin resistance in subset of respondents. So let's go with the numeric test. Basically, we did some kind of visual how they looks like visually, but let me check some numeric statistics so that we will get in the conclusion either they satisfied some of the condition for our research, the ANOVA, and so many other things there later. So formal normality assessment, here we can see with the Sparrow-Wilks normality, I basically tested the Sparrow-Wilk normality and Anderson-Darling normality. So checking with the Sparrow-Wilk normality, I can see that actually this output is from R programming. So the W statistics and p-value given from my R programming, they are listed here in the table. So the respondent age is W statistic is 0.94 something, and the p-value is significantly less than 0.05, right? So it is indicating that the respondent age, right, are different, right? So I mean the normality in the respondent age is violated, right? So they are different. My null hypothesis here in the statistic was the respondent age satisfy the normality, right? But this is rejected. So I can say there is the violation of the normality by the age group. That happens same way with the BMI, with the glucose, with the insulin level. And also, I need at the end that this should be satisfied with the normality so that I can apply my ANOVA test. This is the basic assumption for the ANOVA test, but this is violated here. So again, I checked with the Anderson-Darling test. Is that again the same case? So yes, of course, we have seen there, again, the p-value is significantly less than 0.05. So the hypothesis is now, null hypothesis is rejected. So again, it is indicating that the normality is violated, right? So this is a serious case. So we need to see much more things to make our assumption satisfied with the normality. So still I want to verify with one more steps by checking the skewness, either they still be it is still the same condition. So of course, yes, because it is also shown there in the respondent age and all the way there in glucose and everywhere that you can see the value is greater than 1. That tells the substantial skewness, and that is the case. And I did the log transformations in the table, which is in the below, that you can see there. I transform by the log transformation to check, to just correct my observation to make it normal. But still, I see they are not normally distributed again, even after my transformation, right? So I will do some more things on the way. So let me start with the research questions. That the first research question here is to understand, is there a significant difference in body mass index between males and females? So usually we believe, right? We believe the same age group, kind of males and females, they looks like someone is higher in the weight than the male and the female. So there is a variation between males and females. So we want to know with this data set, is this a difference from males and females with the body mass index on the base of body mass index? Can we say that males and females are different? So here is my hypothesis. Yes, the male and female are different. That is my null hypothesis. But I want to see, is that correct? So my null hypothesis says they are not same, right? So I did the two t-test and two sample t-test. And of course, the one sample is male or the sample is female from the population. And I did that test statistic. Again, the output is from R programming. And here I see the test statistic, the t-value is minus 1.7738 with degree of freedom 22.52. And the p-value that I got here is 0.07. So it is essentially saying that p-value is greater than 0.05. So this is failed to reject the null hypothesis. So we are in the conclusion, the body mass index between male and female is the same with the confidence interval given here. All right. So this is what we wanted to do for the first hand. But now we still want to know, is there a difference between the glucose level and oral glucose level actually, right? So usually the glucose level that we test here is the fasting glucose and the oral glucose, right? So are they same or the different, right? The mean between the fasting glucose and oral glucose is the same or the difference? Usually because I'm interested here, especially to test the PRT test, because we cannot do that with the general traditional T test as they looks dependent, right? Because we do the test, this fasting glucose and oral glucose with the same person and see the different value, right? So these are the dependent observations, right? With the same person, we do the fasting and we do the oral, and that depends with the data set, right, to each other. So we wanted to see here through the PRT test, either they are different or same. And once we run the test and we see the p-value is significantly less than 0.05, right? So it is telling it reject the null hypothesis. So we're saying here they are different, right? So the PRT test is telling us now is the fasting glucose and oral glucose are significantly different to each other, all right? So the next thing that we want to see is now what happens with the BMI. Does that significantly differ with across the groups? That is our major interest of study today. All right. So actually, I was motivated with this paper that was published in one journal, and it is the rate of change in body mass index at another different age during childhood and adult obesity rates. Right. So this paper is actually doing research. Either the body mass index differs according to the one's individual age, right? So the conclusion of this paper was yes, there is a difference between different age for the body mass index. So I wanted to see what this is a very interesting result, because in the different ages, once we grow from the childhood to the adulthood, does the BMI changes? And the research conclude is yes, it is changing, right? So I wanted to see, is that happen with my data set? So does the mean BMI significantly differ across different age groups in this NHANES data set? All right. So for this, of course, I need to go through the hypothesis, which is now I'm telling here is now I'm going to do the ANOVA test, of course, and this is the mean of young, mean of middle age, and mean of the elder. These are actually categorized into three different age groups. My age group population in the age group is now categorized into three different categories, which is young, middle age, and elderly. And I want to see, is that different for the BMI in these three different age groups, right? So my hypothesis is here, no, at least one of them is not different, right? So I wanted to see which is different, and if the first thing is either they are different. If they are different, then my interest would be what ages are actually different. So this is what we are going to do here. So first of all, to test the ANOVA, I should see the data set support me. So they are normal, they are homogeneous in variance, right? There should not be heteroscedasticity, and they must be independent, right? So these are all the assumptions that we do once we do the ANOVA test. So I started doing it through the normality for each group, and it is failed here. The normality is failed. You see, this is from this p-value that we can see is significantly less than 0.05, right? In the young, in the middle age, and in the elderly, in all these samples, we see they significantly less, so that we can conclude the data set that categorize into these three categories, young, middle age, and elderly, they do not satisfy the function of normality. Okay, if this is the case, and if they do not satisfy the normality, right? So then we still can see now the other assumption, what is satisfy the homogeneity of variance? That means is either heteroscedasticity or not, right? So here we go. So we had a violin plot. Inside that you can see there is a box plot, and it's suggesting like a visual, we can say they are not equal variance, right? They have a different variance among these different age group. And also my Levin's test is also supporting my conclusion from the visual, this violin plot is significantly less than 0.05. So it is suggesting there is a violation in the homogeneity. Okay, we will go further and we will see, but we were interested to see if the BMI differs among the age group, right? And we wanted to do here the analysis of variance. And for that, we need to see if the assumptions of the ANOVA are satisfied or not. But we come to the conclusion, both of these assumptions, like of course independence, because they are done with the different individuals, then of course it should be the observations. But other my two homogeneity of variance and then the normality, both are violated. So I cannot actually apply the traditional ANOVA right now, right? Because it violated my assumption. So I was curious now, what next, right? So what do? I wanted to do the ANOVA test, but it is not satisfied. Assumptions are not satisfied. So the option here is to go for the non-parametric type. We could that with the Call-Wallis test, right? So that was one of the options. But still, my presentation today and the focus of study is still to see the ANOVA, right? So the analysis of variance of them. I'm not going to do anything with the non-parametric alternative here. So I'm stick with testing the ANOVA, and I found there is other way that we could do for the ANOVA. Like conditions are not satisfied for the traditional ANOVA, then there is other ANOVA that we can do is Welch ANOVA, right? So this is a different method that we can fix for the degree of freedom, right? So there is a formula to calculate degree of freedom given by the Welch Satterthwaite, and we could incorporate that degree of freedom, and we see through that for the ANOVA. Okay, it is quite interesting. It is, of course, thanks to the Welch. Here you can see the thought from the sitting row here in the front. This guy Welch, the professor Welch, so he published a paper in 19 of generalization of students' problem when several different population of variants are involved. Okay, so he published in this paper like assumptions are not satisfied, then still we can do the ANOVA, and he named that as the Welch ANOVA. All right, so we are going to see that this a particular ANOVA with the data set here. Okay, we still the homogeneity of variance was not satisfied, and also the normality was not satisfied, right? If the homogeneity is not satisfied, the assumption is not satisfied, we could use the Welch ANOVA, but still we could see the assumption of normality is also not satisfied. So here I'm interested to see first by the transformation if I could make the assumption satisfaction of this normality. Okay, the goal is here first see with the transformation if I can transform my observation and if that satisfy my normality condition. So I applied with the log transformation, and I shown that before that was still not satisfying the the normality, right? So I applied here the box transformation, which is actually gives me a little bit better result than the square root transformation and log transformation, where this box transformation is with this formula actually with the transform, apply the transform value, and we get y. If the delta value is equals to 0, this is just like log transformation. But if that delta value is not equals to 0, then this formula gives me like 1 to the delta minus 1 over delta. That gives me the best delta so that I can apply that delta and transform my observations. Okay, so the output, actually the result from R programming again, and the likelihood value for this box transformation is shown in the graph here. So here we wanted to see where is the peak value in my different delta value. Okay, so ranging from -2 to 2 with a different delta value, I see the peak value is somewhere in this point, which is like 0 point minus, right? So the negative 0.7 somewhere, right? So we can see there is a peak in this particular value, minus 0.7. So I choose that minus 0.7 and transform the this box Cox. Okay, then I saw this plot here. We can see like after the box Cox transformation that is shown in the second figure here, this is somehow still it is not perfectly normal, but we can say, oh, this is normal. In the behavior, it is still not that normal, but it is so far satisfying the normal in most of the cases, right? So now our outcome up to this point is our data was not satisfied with the normality and then the homogeneity of the variance, right? But we somehow transform our data, and now we can say our data satisfied the normality, right? And we are applying the Welch ANOVA so that we don't worry about either this satisfy the homogeneity or not. So we are going further to test young population and elderly population, right? And then the middle-aged population are same expect to BMI or not. because we are now somehow making the assumptions are satisfied. Okay, you could still see the satisfaction of the normality condition here through the box-Cox transformation with the test statistic. The first statistic in the left side, the best value that we got is not satisfying the normality. But in the second, after doing the box-Cox, somehow close to 0.05, right? So we could say, okay, this somehow visual like we see that before, right? So with the test also we can see, okay, somehow normality condition. All right, so we can go further and test. And here we see, okay, here is my output from the R here. And this is the standard ANOVA. You just apply the standard ANOVA, my p-value is significantly less than 0.05. It still says, okay, the difference, right? The null hypothesis is rejected and there is a difference between the age group, right? But our main interest is to see the Welch ANOVA, right? Still, the standard ANOVA is also giving output as we wanted to see, right? And that is satisfied, but there is an Welch ANOVA that perform best in case of this violation of normality. So this here, like it is, we can see the value is significantly less. So that means the difference age group definitely are different, right? The different category of age, we see the difference of BMI. All right. So we go for the Tukey's and analysis here and the Games Hall post hoc test to see which age group are different. We know up to this point now, okay, the group are different, right? We see from the Welch ANOVA, but what are the difference? Which of these age groups are different, right? And what is the level of their difference? We want to see that. And Tukey's HSD also show the difference between these this group, but we rely on this Games Howell post hoc test because this is more relevant once we do the Welch ANOVA. Okay, so if we were just doing a traditional ANOVA, then Tukey's HSD could be the better fit. But for the ANOVA, the Games Howell postdoc test is the one to analyze what are the different age group. Here we see the Cohen's d minus 0.61, right? Something for the young versus middle aged. So if our Cohen's d value is less than 0.2, then we say there is a less effect between the categories. If there is the value 0.5, then we would say this is a kind of effect. Okay, but this is greater than 0.5, then we would say there is a significance between the category. So in the first young and middle age, we see this is the value greater than 0.5, right? So this is actually, of course, talking about the absolute value. So this is greater than 0.5, right? So it is emphasizing youngs versus middle age. It is mostly we can see there is a difference in young and middle aged, right? There is a high effect of youngs and middle aged population. Okay, in youngs and elderly, there is also a kind of high level of effect of among the variables, two categories. But in middle age and elderly age, there is not that significant difference between these two age groups, right? So it is indicating somehow less effect between this middle age and elderly age. Okay. See that through this visual as well, we can see the confidence interval between these different age groups. We see from this plot, like the age and the elderly, they are somehow overlapping, right? So it is essentially supporting my output just before. They are not that significantly different. But if you go with the young and compare with these others, then you see the significance difference between them, right? So we say, okay, there is significant difference between young, middle-aged, and young elderly, but we still wanted to understand what happens with the average of young and middle-aged with the elderly, or the young and elderly with the middle-aged, right? What happens with the average of between them? So we could do that with the comparison, with the contrast with the young, middle-aged, and elderly. But we see that young and middle age is also going to be very clearly different from the elderly, because the if on young with other category is significantly high. So we want to see, of course, we want to see here with this hypothesis now, is there a significant difference in the distribution of BMI categories? Now we are interested to see if there is a significant difference in BMI category across the age groups. Okay, so I categorize this age group according to BMI here, and these categories are now underweight, normal, overweight, and obese. So these are from the WHO. Usually, I categorize, I filter these observations according to WHO. It says if this is less than 18.5, then they are underweight, and if this is between 18 and 25, 18.5 and 25, then this is normal, and so on. Okay, so in my data set, there are 87 underweight value. There are 795 normal, and of course there is 6 obese and so on. Okay, so I wanted to see here now, is there a the distribution of BMI categories across the different age group? Okay, so this factor I saw output here through the ANOVA, like there is significant difference between age groups. The p-value, it looks like, is significantly less than 0.05. So it is supporting that there is a difference between the age groups, right? So the research that was done before with a journal that I was shown before, so also satisfied that research outcome from that to data set as well. Okay. Yes, here is a result output that we see the value is significantly less, right? So this is the value is significantly less than 0.05. It is essentially saying there is a significant difference between the groups categorized in BMI. Okay, so now if the difference between these BMI categories, then between these groups, then what actually are different? Which of these categories are different? Okay, so this is our next area of interest. And then here we see through the pairwise comparison with Games-Sowell test again, we see the normal and the underweight. The value between normal and underweight, the p-value is here 0.5. It is essentially saying, okay, the normal weight and the normal weight and the underweight between these two weight, there is not that significant difference, right? They looks pretty similar. But if you go with the obese and underweight, this is significantly less, right? So this is a high effect on obese and underweight, right? So the BMI between and the underweight is significantly high. There is a significant difference between them. And likewise, you could compare overweight and normal and obese and normal. So there looks like only the normal and underweight is not significantly different. Rest of others are different, right? The rest of others are significantly different to each other. We also see like obese and overweight is also not significantly different if we are talking about 95% confident interval. Okay. So now my other area of interest is to see does the BMI category and recreational influence oral level while accounting for gender as a block. So I want to make a block, right? Because I want gender impact with those categories, then that would definitely mislead my outcome, right? My result. So I keep a block for the gender and checking the the categories and recreational level, right? So there are two. I already told in the first slide, maybe there is a recreational category, and which are the two different levels. This is the first is the level 1 and the level 2, and this level is actually for how much the one is involved with recreational activities like sports or gym type of activities. Okay, so of them, is there a difference of BMI categories, right? So we will check that, right? So here the factors in the model are, of course, the BMI categories and recreational level, where in BMI category we have underweight, normal, and overweight, obese, and then recreation has level 2, and my blocking category is with the gender, which is male and female. So my hypothesis now is there is no effect between BMI category, right? And there is no effect on my recreational level. There is no any interaction between gender and blocking, between BMI and recreational level, and there is an effect of the gender blocking level. So my all hypotheses are telling there is no difference between everything, right? So now I want to see, is that true, or is there a significant difference at least between one of them or all of them? Okay. So model here is the ANOVA model here is a block design with the two factors, and here is my block design. This where the mu value is, of course, the mean in my observation, and this tau I is the effect on ith BMI category, and gamma k is the blocking effect on the k gender, right? And of course, the bj is the effect due to jth recreational level, and then tau beta ij is the interaction effect between the BMI category and recreational level. And of course, there is an error which is incorporated with epsilon ijk, and this error is assumed to be normally distributed, and this is the mean zero and the variance sigma square. Okay, so the output here after this hypothesis, there is the difference between BMI category. See, there is a significant difference in the BMI category. My p-value is suggesting me is significantly less than 0.05. So it is significantly within the BMI category. So the factor is like to each other. And recreational is also different comparing with the two level 1 and level 2. This is different. And also, once we see the gender, actually gender do not make any right? So either male or female, they would have the same the output, right? So the value is here, of course, the greater than 0.05, and it is suggesting there is no significant difference between the gender. Okay, and of course there is no any interaction between BMI and recreation. So we wanted to see if there would be a different value in my glucose level if one is with recreation and BMI, but there is no significant difference on the interaction. So here my conclusion is there is no interaction between BMI and recreation. There is no interaction with, there is no effect of gender, but there is a significant effect in recreation and the BMI category. Okay. So I see like making a block for the gender is not helping me, right? Because this is rejected. There is no interaction, there is no effect of gender. So relative efficiency of making gender as a block without making it, right? Just a completed randomized design or just a block and doing a randomized design. But I see the relative efficiency is even less than 0, right? This is 0.89, which is suggesting me like the gender has no effect, and it is suggested to remove the gender block from the the model. Okay, so essentially the output here is there is a difference between BMI category and recreation, and of course there is no need of making the gender, and there is no interaction between BMI and okay. And now here is the profile plot. It is essentially the plot between the category and recreational level, and they are parallel, right? There is no any kind of interaction, and there is a kind of parallel we can see between this BMI category and the recreational level that we just seen through the test before, right? So we have seen the same thing here, and this is how this looks like. All right, so this is my end of the presentation. So basically we wanted to see if there is a difference between different BMI categories and recreational level by making a block of gender, and before we did, is there a significant difference between the age groups and the BMI, right? Is there a significant difference between the glucose levels and the age groups? So most of this analysis, and we come to my presentation today. Thank you very much. Is there any question? I'm happy to answer this.
Yeah, thank you for your presentation, and I hope this presentation is wonderful, and this might be useful for practicing statisticians, mathematician, computer scientist, and even economist. So yeah, most of the things are very important for me, I think, but there are some queries. Yeah, I have a little bit insight. So can you go to the homogeneity of variance?
Yes.
Yeah, here. The first time I saw this Bayesian plot. So is there some difference between the usual box plot and then this Bayesian plot? So can you tell me, is there any difference or just simply the fancy on what you hear?
This basically the Bayesian plot is how they are distributed, right? So you see here, this looks like more distributed, right? So this is more flattened.
Okay,
That's how it works. Likewise,
yeah, I mean,
in the box plot, if the lower interquartile, the lower and upper between them, how variation that they looks, and the same way we do with the Bayesian. Sometimes it will be to see through the Bayesian plot even better than the box plot. Right, so we could both of them, and I incorporate both of these things together.
So another one last question is ANOVA table.
You mean which ANOVA table?
Yeah, I think it's last.
Okay.
Or last second. There might be.
Is this?
Yeah. This studied various sources of variation, and you calculated the relative efficiency. So how do you calculate the relative efficiency? Is there some
Yes, of course.
formula, or how do you calculate this one?
Yes, the relative efficiency is basically we are checking this, is there a significant importance of blocking variable or not? This is how reason that we check the relative efficiency. And if we do not make a block, then what that becomes? The model is just the completely randomized design model, right? But once you do the blocking, then that becomes the completely randomized design with block.
Or you mean the ratio between block design F value and randomized design F value?
Not only the F value, actually it is the mean square error, right? So we want to see what is the errors that you get without block design and with a block design. If you get the value is significantly higher because you are checking the ratio between block design and without block design. And if you see the error is greater than 1, then you would say, oh, making the make sense, right? But if you are getting a higher value like 15, 20, 30, or 100, like if you're getting the value bigger than 1, then you would say the making a block design is more important than without making it, right? So it is suggesting you not to include that gender as a block design.
Awesome. Thank you very much for your answers.
All right.